Hi everyone, this is Mr. Lee. In this video, we are going to be looking at motion graphs and the skills necessary to identify an object's motion. All right, so let's begin. The first graph that we want to go over is the position time graph. For the position time graph, we are looking at just the slope, and the slope represents the velocity. So as a quick reminder of how we know this, right? So let's say we have a position time graph here. And this is a good little skill set that should help you out for any kinds of graphs in the future, even though we're just talking about motion graphs. So the y-axis variable is position, the units are meters, and the x-axis variable is time, and the units are in seconds. So let's say we have a graph that looks something like this. The slope, the way that we find slope, right? So slope is equal to the change in the y-axis over or divided by the change in the x-axis. So the change in the y-axis is delta x over the change in the x-axis, which is delta t. Okay, so this right here is part of a formula. And the reason why units are so helpful is, let's say you're not quite sure what formula delta x over delta t is, we can put the units there. That gives us meters per second. And so hopefully the units give you an insight into what that represents. All right? And we know that the formula for velocity is delta x over delta t. Therefore, the slope is equal to the velocity. All right, let's go on to the velocity time graphs. Same idea, right? I'm going to do a quick sketch of a velocity time graph. All right, and we'll just draw the same kind of line. All right, so let's do the same idea with slope. Okay, so the change in the y-axis is delta v, the change in the x-axis is delta t, right? And this gives us meters per second, and that is the formula for acceleration. So that's how we know that the slope represents acceleration. All right, now area under the curve, same idea. Area under the curve, or area, is just base times height. And the base axis, or the x-axis, times the y-axis. And our base axis here is time, and the y-axis is velocity, right? So we have to think, all right, what formula are we multiplying velocity times time? And that actually comes from the formula from before, this formula right there. So if we take that formula and we get this time variable here, multiply on the other side, we get velocity times the change in time is equal to delta x. Therefore, velocity times time gives us displacement. So the area under the curve here is displacement. And because this is a skill that we're going to be doing in the future, I'm going to show you, right? So this area in the curve right here that I just shaded in, that represents the displacement. Okay, so let's use the unit trick to show you that you can even do that with area under the curve. So we know that the units for time is in seconds, and the units for velocity is meters per second. So if we do seconds times meters per second, this cancels out in the numerator and denominator, leaving us with just meters, which is the units for displacement. Boom. All right. Now we have acceleration times time. The acceleration times time, there is no slope value, and the area under the curve represents the change in velocity. Okay. All right, so on the left are the steps that I highly recommend for identifying the types of like graphs, what the graphs represents. So these are your MCQ type of questions that you'll see. And the FRQs are a little bit more in depth, but the steps and the skills are the same. So I'm not going to go over the steps individually, but what I will do is I will do a example with you and identify the steps as I'm doing them. Okay. So let's say we have a position time graph, and the position time graph looks something like this. All right, so do a quick sketch. We already did step one. We looked at the graph and we're like, okay, so this is a position time graph, And let's do step 2. So step 2, we're looking at the positive and the negative regions, right? So because we're in quadrant 1, this is all positive up here, and down here this is all negative. But because the line is mainly in the positive region, we're going to say we're in the positive region. So what this means is that the object's position only remained in the positive position. Okay, so if this were like a FRQ and we had to write stuff out, we could even include that, and so I'll do that down here. So we can say the object's position remained in the positive region. All right. Next, you're going to identify what does the slope or the area of the curve represents. And so because this is just a position time graph, we only have to worry about slope. And the slope represents velocity. Okay, so I'm going to go straight to step 4. Now what we're going to do is we're going to draw tangent lines at the very beginning of the journey and at the very end. So the very beginning would be right around where time is equal to 0. So I'm going to draw a tangent line right there. Okay, and then I'm going to draw a slope right over here. So what we're looking for is what's happening with the tangent lines. Okay, so are the tangent lines getting more steep? Are the tangent lines getting more flat? Okay, so those are the things that we need to be identifying. So let's write that down over here. This is not part of the description, but the ideas. So a steep slope means greater magnitude. Okay, a flat slope means a small magnitude. So we take a look at this graph and we see that the slope, even though it's pointing downwards or the negative, it's pretty steep, and then it goes from steep to flat. And so the cool thing about this trick is all you have to do is replace the word slope with what the slope represents. So we can say here in the beginning, the object had a fast negative velocity, but then the velocity decreased, right? And we know that because the line is getting flat and approached a velocity of 0. And so we know that because anything with a flat line or a flat slope represents 0. So there is no rise, right? There's a run, but there's no rise. And so we can say the object had a fast negative velocity, but then the velocity decreased and approached the velocity of 0. All right. So I'm going to pick up my pen. I'm going to show you a cool, nifty little shorthand trick. Right, so whenever we do these as FRQs, we have to perform a explanation or a justification. So we say therefore. So instead of writing out the word therefore, look at these dots, dot, 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 in a triangle. This represents the word therefore. It's shorthand, so you're not writing therefore, every time you're doing an FRQ. Therefore, now we have to think. All right, if the object slowed down, okay. Then there's a couple of things that we know. We can say therefore, let's see, the object experienced a, so let's think about this. So the slope is pointing in the negative direction, so the velocity is negative, but the object slowed down. So we know that the object slows down when the acceleration and the velocity signs are different from each other. So the object experienced a negative acceleration. Okay, because the velocity the object experienced a positive acceleration because the velocity was negative, but the velocity approached 0. And then we can say even came to rest. So that's a phrase you'll see a lot in physics. Came to rest. That means that you slowed down to a complete stop. All right. Okay. So now let's do one for area under the curve and slope. Okay, this is good practice. We just did a position time graph one, so we'll do a velocity time graph one, because velocity time graph, that's the one that we have a lot of problems with. And the reason why we have a lot of problems with velocity time is because it has both slope and area under the curve. Okay, so let's take a look here. Boom, boom. All right. Take a look at my line. Okay, so the first thing that you should do, according to my list, is you're going to draw in your area under the curve shapes. All right, so I'm going to show you that technique right now, and let me go into the explanation as to why that's important. So here we have this velocity time graph, and I'm going to shade in my area in the curve. So to shade in the area in the curve, you go from the line itself and you go to the x-axis like this, going to the x-axis. Now, because we already performed step 1, we know that all this velocity is in the negative region. So I'm going to just jot that down. All this velocity is in the negative region, and because that velocity is in the negative region when we do our multiplication, all of this area under the curve is negative. Whoa, look at that. Okay, now I'm actually going to switch colors so that you can see this a little bit better. Now I'm going to create this shape here. Okay. Look at that, it's a triangle. Now, there will be problems where if you know this trick, that makes your MCQs a lot easier to do. So a very common type of problem that you'll see for AP Physics 1 is that this area under the curve right there, that triangle, which is negative, and this area under the curve right here are the exact same area. And so why that's useful is because if we added up this area with this area, we get a total area of 0, which means that you don't have to do all that calculation because you already know that when you add up the two areas, you get 0. So what that means for us is that the only area you have to actually calculate would be this rectangle here. All right. So if we are doing our thought processes, we can say for a velocity time graph, the AUC is displacement, and then we can say the object has a positive displacement, right? And if we figured out what that area is, we could even write that that displacement. Let's just pretend like it's 20 meters, right? So it was 20 meters from the start, and we know it's positive because it's above the y-axis. Okay, or excuse me, it's positive because it's above the x-axis. Okay, so this thing that we're going to do is we're going to look at the velocity time graph, just practicing the same skills that we covered before, but for slope, right? So I'm going to just draw a line that we saw before, so we have this line here. Okay, so the skills are the same, even though we have a straight line. I'm going to draw the tangent line in the beginning, right? I'm going to draw a tangent line at the end. Okay, so one thing that I know is that the slope for a velocity time graph represents acceleration, and it looks like the slope does not change. So I'm going to write that down. The slope for the velocity time graph does not change. Okay, and now is a great time for us to use our therefore statement, right? So imagine my triangle dots. Okay, therefore, the acceleration has a constant slope. Or excuse me, therefore the acceleration is constant. All right, and we know that because the slope for a velocity time graph represents acceleration. Now this is where the identifying the positive and the negative regions really help. So let's pick up the pen again and let's go back here. So we know that here, for this part, the velocity is negative, right? And then for here, the velocity is positive. Now, see how powerful this idea is. So we know that the slope is positive, okay? So this tells us that we have a acceleration that is positive throughout the entire thing. So over here, our velocity is negative, but our acceleration is positive. So what this means is that the object is slowing down. And we know it's slowing down because look at this point right here. That's a velocity of 0 right there. Let me highlight it. That's a velocity of 0. And so if your velocity is 0, that means you come to rest. So this object was going pretty fast. It slowed down, and we know it slowed down because it reached the velocity of 0. And then after that, over here in this region, our velocity is positive and our acceleration is positive. Therefore, we sped up. And we know that because we are starting from rest over here, and our velocity just keeps on increasing in value. Okay, so if you remember from the velocity acceleration video, one of the common misconceptions that students have is that a negative velocity means that you are slow, but remember, negative just means direction. And it's very important because over here, this value here, let's say this is velocity of -20, right? Versus like, let's say like right here, let's say this velocity is -1. Even though this -20 is a very big negative number, they're still going pretty fast. Okay, they are going a lot faster than this -1. That negative simply means that they're going in the negative direction. Okay, and so they're going pretty fast, and they slow down, slow down, slow down until they come to rest and they speed up again. Cool. So we could even write that in our statement. We can say the object starts off with a negative velocity, but slows down, comes to rest, and then speeds up in the positive direction. Ta-da! And that's it. That's how we read motion graphs. So as a quick reminder, the skills and the little techniques that I identified here, okay, this is what we'll be practicing throughout the entire year and in class. So make sure you jot that down so that we can have it as a reference. I'll see you next time. Bye-bye.